Hi, Tony Fowler again. This is the second video of two talking about my easy lift drill press table. If you haven't seen the first video of these two, I suggest you stop watching this one now and go and look at the first, because otherwise this video won't make any sense. The link for the first video will be in the comments below. This is a diagram of the drill press. We've got the column up here. This is the table. This is where it's normally clamped on. Now it's 205 millimeters to the center where the drill bit comes down, and just to keep things simple, let's assume that that's where the center of gravity is. In fact, it's going to be back a little bit more because this has a little bit more weight proportionally, although it's thicker, but it's also narrower. So it's not that much different. The edge of the table is 300 millimeters away from the center of the column, and the depth of the column is 75 millimeters. Now, as we saw in the first video, when I slackened off the clamp here, the table neither moved up nor down, but if I applied just a finger load at this point, the table just came crashing down. So I was pushing up and the table came down. Let's look at why that happened. We've got a load on here that puts a twisting moment on the table in this way, and that moment is resisted by an equal and opposite moment that this clamp part exerts on the column. We can easily calculate what the forces are here. This is 75 millimeters, this is 205. Let's assume that we've got a 10 kilogram load pressing down here. That 10 kilogram load on here includes the weight of the table, a vise, and any workpiece that we've got on there at the time. Of course, this will vary depending on what work we've got on there, what vise we've got, or other holding features. But this is a round average for this particular drill press. We can get an idea of the function of it by just taking a nice even figure like 10 kilograms. So we've got a lever arm here of 205, we've got 205 millimeters, we've got 10 kilograms force pushing down, so we've got a moment caused by this equal to 2050, 10 multiplied by 205. Now that has to be resisted by a couple here that's only spaced 75 millimeters apart. So we divide this by 75, we get a value of 27.33. Now that is a force here. There's a force that the table is acting on the column in this direction here and this direction here. You can see you pull down, you're going to push there and push in the opposite direction there. Now each of these forces is 27.33 kilograms force. Now that creates a friction force of this on the column. Now the actual friction force will depend on the level of the coefficient of friction. If we look in reference books and things, it averages out the coefficient of friction of cast iron on steel. It's a steel column, cast iron table, and it averages out, if it's dry, at round about 0.4. If it's well lubricated, it may well be about half of that, but we'll just go with this for the moment. So we've got this couple on here, which results in a force 27.33 in two places. So if we multiply that by the coefficient of friction, we've got 27.33 times 0.4. Now each one of these forces at the top and bottom add separately to the total friction, so we need to multiply that by 2, and that comes out to approximately 22. So a bit more than double what we've got there. So that's why the table just stays there, because this causes a friction force on here which is over double the force that's pushing down on here. So why, when I just put a finger force here, did it come crashing down? Simply because when I put a force up here, it reduced this moment, and hence it reduced these lateral forces, and it reduced the friction force. Now, as long as the friction force is less than the sum of the vertical forces acting on the table elsewhere, then it will move downwards. So we've got a certain force here to relieve the friction on here. So, and that calculates out to, depending on the value that we pick for the coefficient of friction, around about 5 kilograms force. I think that that's more than I was applying with my finger to get it to come down. So basically what that indicates is the actual coefficient of friction on my drill at the time that I did it was probably less than 0.4. But this shows the physics and principles involved. So in this case, if we apply a 5 kilogram force here, that would remove enough of the moment here so that the friction force was less than the net force here, which would be 10 down, 5 up. So we're left with 5 down. So as long as we applied enough here to reduce the friction on here to a level below 5, then the remaining 5 kilograms force acting downwards will be enough to send the table crashing down, as we saw in the first video. Well, we've seen it with the drill in the standard form. It's very easy to get the table to come down. We just apply a relatively small lift force on the front. It seems counterintuitive. We press up and it comes down. So we just apply a small force here and it will come down. Very easy. We can just take the force off when we want to stop, and it will. So how do we get the table up? It seems crazy. So just say we put more force on here so that we balance the total load coming down. So we'd have to put greater than 10 kilogram force on here. So what happens then? That creates a moment of 300 times, well, greater than 10, say 3,000. So, but that's in the opposite direction. So what we're trying to do now is to twist the table like so. We'll have the forces acting instead of at the bottom, at the front, and the top at the back. It'll be the other way round. It'll be here and there. But we've still got a jamming moment on here. It's rather like a drawer in a chest of drawers, you get a little bit crooked and it jams. It's the same sort of mechanism here. So by putting a higher force here, all we can do basically is stop the table falling like it was. But how do we get it up? Well, we have to balance out this 10 kilograms force for a start. So again, we need to put a force of 10 kilograms at least. Well, we need a total upward force of greater than 10 kilograms. But we saw before that we need something less than that. Just say 5 kilograms force, for example. That will leave the moment on here. So now we need to get an extra 5 kilograms force acting upwards in order to get it to move. Now, we don't want to add to the moment anymore or reverse its direction. So what we need to do is to pull up here. And that's essentially what was necessary with this drill and many others that don't have some other either powered or rack and pinion mechanism for lifting it up. So basically what I had to do here was put one hand here to supply most of the residual force, and then I'd lift at the front. So I had to lift it both places in order to get it to move up. Basically I'm carrying the load through two load positions, but 10 kilograms force is quite a bit to just lift up, especially when you're as ancient as I am. And if you've got an extra heavy workpiece or a bigger vise, a bigger holding fixture, it's even more. It wasn't easy to do. So let's have a look at what I did to fix it. And as you saw in the part 1 of the video, it became so easy to move it that I actually prefer it to having a rack and pinion system. I had been considering putting all sorts of mechanisms on it to lift it, like a rack and pinion, or perhaps I was going to wind a cable around a drum and wind it up that way. So what I did to get round this rather non-ideal method of being able to raise and lower the table, particularly when I had a heavy workpiece on there, then it was quite an effort to lift it up, even though it was done with two hands. I counterweighted it. Now there's nothing new in counterweighting machinery. Milling machines, smaller ones, quite often come from the factory with counter weights fitted to the rear or inside the column, something like that, and it's certainly not unknown for drill presses. I think what I did here was apply a little bit more science to it rather than just adding a counterweight and hoping for the best. So what I did, just for neatness, this part wasn't necessary, but I put a pulley up here so that I could put a cable with the weight on down through the centre of the column. It just keeps it neater rather than a cable and weight flapping about externally. Now it was a while ago that I did this, and I can't remember exactly the weight of the counterweight here, but it was something 12 or 14 kilograms. It was quite a bit more than the sort of lower level of the load on the table of 10 kilograms. I bolted a plate out here on the back, and the cable fixed to it 65 millimeters away from the center of the column. Now that has a force pointing upwards. The cable is pulling on the table in this direction, opposite to where our load is. But that is reinforced, so that creates a moment of this force, say 12 kilograms times 67, that creates a moment of 804, which is added to the moment that we saw before of 2050, which was due to this 10 kilograms here. So it looks like we've actually made the situation worse. And but as you saw in video number 1, the system works quite well. We increase the moment, but also the overall thing works much better, as we'll see. This detrimental effect of this moment from this cable at the back could easily be changed if the cable was at the front of the column, because then this moment would be in the opposite direction and would tend to counterbalance some of this. The trouble with that is, if we've got a cable down the front of the column, we're in effect reducing the workspace that we've got on the drill table, and on things like this you never have enough. So this works quite well, and like most design, it's a compromise between all the factors involved. So now let's see what we have to do to get the table to move both up and down. Originally, if I just applied an upward force at the edge of the table, we saw that it would come crashing down, because this would be less than 10 kilograms, say, well, I was talking before about 5, so we've got a net 5 down. So when the moment's released, there's 5 kilograms trying to push the table down. But now we've got this constant force of 12 acting upwards due to this weight. So we've got a surplus of 2, say, trying to lift the table up. So all we need to do is reduce this moment enough to reduce the friction force to less than the net force acting upwards. So we can just apply, now we apply an upward force. If it's of the similar level as before, which sent it crashing down, what's going to happen now is we've got a net force of 2 kilograms wanting to lift the table up. Now it doesn't go shooting up like it did when it was coming down, where we had gravity yanking it downwards, and it's very easy to control because of this. If we modulate this force, and I do it just with one finger now, I showed that on the first video, but it is also how I use it in practice, just a finger touch with the heaviest workpiece that I've come across so far. That's all that's necessary. Right, so we saw before that we could make it go in one direction but not too good in the other direction. So we can see now we push up and the table goes up. Quite intuitive. How do we get the table to move downwards? If we push downwards on here, that's going to increase the jamming moment here, and so the table's going to be locked. As I showed in the video, it didn't matter how hard I tried pulling that down. If I was anywhere in front of the centre of the column, it wouldn't move. But I put this plate out the back. It's 300 millimeters away from the, well, there's a hole in it, 300 millimeters away from the centre, just the same as to the edge of that. But it could be any other number. But now if I apply a force here downwards, not on this side, but on this side, this force will be trying to relieve this moment, but it will also be adding to the force to push the table downwards. So if I apply enough force on here to overcome some of this moment, enough to reduce the friction sufficiently, then the table will move down as long as this force is greater than the net force from these two, which is only 2 kilograms. Well, to relieve the moment is probably more than 2 kilograms I have to push here, so we're well covered from the net vertical force point of view. It's just a question of relieving the moment on the column. So I can just push one-handed behind the column and it moves the table down. And one finger push up here on the front of the table lifts the table up. But for coming down, it can be even easier. I can do it with less force on here. If I still apply a finger force on the front of the table and push down on here at the back, then those two are working to relieve that moment, and it's very easy to have it jammed or free just with that. So it gives me a very sensitive feel for moving the table up, stopping where I want it, moving the table down and stopping where I want it. And as you saw in the first video, it's ever so easy to use. I can't think of a simpler system other than one that's motorised, which is a little bit over the top for a drill press of that size. There's just one last thing. You'll remember that in the first video towards the end, I showed that I put a small 1.5 kilogram weight on the end of this plate here, like so. That was 1.5 kilograms. It was only 1.5 because that was the amount of lead I had left after casting the main weight here. It could have done with being more, because see what the effect of that is. If that was a bit more, this is creating a moment on the column this way. This is creating one in the opposite direction, so they're tending to cancel each other out. So if this was quite a bit more massive, it would cancel it out. Well, you could have it so the moment was virtually zero to start with, and so assuming we had this load, we didn't change the load on the table, we could have basically zero moment here in its static position. But then what we would have is, well, I've shown that at 300, but let's say it was at 205, just to make things simpler, and this was a 10 kilogram weight, just like this one, then the moments would be completely balanced out. So then what we would have to do, though, instead of sort of applying another vertical force with our hands and also with the cable, we'd have 10 kilograms here and 10 kilograms there, but we'd have the jamming moment removed. So all we'd have to do is just supply enough up and down force to move the table where we want it, and that was just a question of getting an average value in here for this weight. Well, that's all there is. As I often say after the end of the "Isn't physics fun?" Bye for now, see you in the next video. If you like this video or any of the others, please share, subscribe to my channel, and don't forget to click the button to receive updates of any other videos. Thanks for watching.